Hello, my name is Ken Bondy. I'm a structural engineer. I've had a long career as a specialist in the design and construction of post-tension concrete building structures. My career has spanned almost the entire history of American post-tension building construction. And today, I'm going to walk you through what I consider to be the highlights of my career in post-tensioning. I was very flattered when my son, Dirk Bondy, asked me to do this. It will be similar to what I wrote in chapter 1 of Dirk and Brian Allred's magnificent book, Post-Tension Concrete Principles and Practice. So let's get started with a trip back to 1963. Oh, that's a long time ago. It was the fall of 1963. Oh, I hate this part. I was 23 years old. That tells you how old I am. I had completed my Master of Science in Civil Engineering coursework at UCLA. I was almost finished with my thesis. Interestingly enough, I wrote my thesis on finite element techniques. I was living on a very meager teaching assistant salary, and all things considered, it was time to get a job. I grew up in the Los Angeles area. I was born in Chicago, but I grew up in Los Angeles, in a part of Los Angeles called the San Fernando Valley, which is the north part of LA. And I was hoping that perhaps my first job could be in the San Fernando Valley, close to home. So out came the Yellow Pages, and I checked to see if there were any structural firms that were hiring in the San Fernando Valley. There were. I interviewed all of them, and I was actually hired by one. I was really impressed with one of the firms, and the gentleman who interviewed me. The name of the company was T.Y. Lin and Associates. I had no idea how important that first job was. A lot of times we come to a crossroad in our life, and everything after that is changed by the direction we take, and the decision doesn't seem so important at the time, but the decision to go to work for T.Y. Lin and Associates would change my entire life. I didn't know that they were a pioneering firm, the pioneering firm, American firm in prestressed concrete. Working for them started a long career as a specialist in post-tension concrete design and construction, and it offered me a bunch of fantastic opportunities, not the least of which was that I learned about post-tensioning from the most respected individual in the history of the industry, and that would be T.Y. himself. It was an exciting time in post-tension concrete. It had been used in buildings for only a few years. The first post-tension buildings were in the mid-1950s, so a little less than 10 years before, and it had been used mostly at that time in lift-slab construction, which we'll talk about later. Prestressed concrete had just been introduced into the ACI Building Code, the 1963 edition, for the first time. And as I said, in the next 50 years, plus years, my career has spanned every major landmark in the development of post-tension concrete in buildings. It's interesting that the American post-tensioning industry owes its existence to lift-slab construction. The first lift-slab buildings in the United States were built in the mid-1950s, and they used non-prestressed slabs. In lift-slab construction, the columns are the first thing that's done is that the columns are erected full height, and they were either steel or concrete. The slabs were cast in a big pile on the ground, one on top of the other. Then the slabs were lifted into place by jacks and cables that were attached to the tops of the columns. Then the slabs were secured at each level to columns by various systems of pins and brackets. It was a highly successful type of construction with a few exceptions. There were problems with deflection and slab weight in the long two-way spans. And to solve the deflection and weight problems, the lift slabs companies all decided to change to post-tension slabs. And the reason they did that is that the slab weight would be reduced by about 30%, and it would eliminate most of the dead load deflection. Problem was there weren't any existing American post-tensioning systems. The lift slab companies therefore went to Europe for help. Most of the existing European hardware was for large grouted multi-strand tendons in bridges, like the Fresnel system and the Manuel system. The only European system that was feasible for building construction with light unbonded tendons was what was called the BBRV button-headed tendon system. And the B and the B and the R and the V stood for four Swiss gentlemen who collectively invented the button-headed tendon system. And thus we entered into the button-headed tendon era. Each lift slab company returned from Europe with a license to market the button-headed tendon system. Some independent companies like Prescon, Ryerson, and a few others also obtained button-headed tendon BBRV licenses just to market the post-tensioning system itself. Here's what it looked like. It was a monstrosity. It consisted of a grouping of quarter-inch diameter wires. They conformed to ASTM. They were quarter-inch diameter wires, 240 KSI ultimate strength. The wires passed through a steel bearing plate, and they also then passed through a circular stressing washer, which was externally threaded so the jack could grab onto it. The wires had cold formed buttons banged onto the end of them in a mechanical process by impact, and that would hold the force. It would develop the force in the quarter-inch diameter wires against the stressing washer. When the time for stressing took place, the stressing washer, the jack attached to the stressing washer, stressed the tendon to the proper elongation. Shims were then inserted between the back of the stressing washer and the front of the bearing plate, and that held the elongation and the force in the tendon. Now, you'll notice a couple of potential problems with this anchorage. The anchorage solved deflection problems, but the button-headed tendons created other problems. Because both the stressing and the dead-end anchors had to be attached in the factory, that required quote-unquote exact length. There was no tolerance for adjustment if the length was wrong, the length between forms was wrong. They also required stressing pockets, of course, to cover the shims. The anchorage couldn't be placed outside, obviously, the slab. It had to be placed inside the slab and then later covered with either a continuous pour strip or a stressing pocket. It also required bulky and expensive couplers when intermediate stressing was required. The first Strand post-tensioning system was introduced in 1962, and it was developed by one of the most famous names in the history of concrete construction in this country, Edward K. Rice, Ed Rice. He was the president of T.Y. Lin and Associates at the time, and T.Y. Lin consulted for precast companies, which all, of course, used 7-wire strand for their pre-tensioning steel. The Strand post-tensioning system was introduced by Atlas Prestressing Corporation, which was a company I went to work for in 1965, and at which time Ed Rice was the president of of Atlas. Excuse me. Let me go back and say that again. It was introduced by Atlas Prestressing Corporation, a company that I did go to work for in 1965. Ed was at the time president of T.Y. Lin and Associates. The strand system did not require precise length. The tendons could be cut several feet longer than the concrete length. They did not require stressing pockets, and I'll show you a picture of why that's true. They did not require couplers. If intermediate stressing was required, which it was on almost every project, the intermediate anchors could just be slid on to the strand. The strand was cut the full length of the building, and the anchorages were just slid on to the intermediate stressing point. This is what the first strand wedge anchorage that was ever used in the US looked like. As you can see, well, maybe you can't. This kind of looks like a bearing plate, but it's not. It's just a plate that's used to nail the coil anchorage onto the edge form. The force in the cable is held by two cone-shaped wedges with teeth that penetrate the strand, the 7-wire strand, and the force in the strand then is resisted in bursting by the coil of wires. It's kind of an unusual design, and I think I've talked to Ed about how he came up with it, and it had to do with some large coil type anchors that were used by Fresnay in Europe at the same time. Nonetheless, this was the very first strand wedge anchorage that was ever used in the United States. And since it relied on the tensile strength of concrete, there were tons of breakouts that occurred in the early days of a wedge post-tensioning with the coil anchorages. And that was particularly true in lightweight concrete, which was prevalent in building construction at that time. I remember in the early Atlas days, we would often gather after work and discuss the events of the day. And our field superintendent, Tom Anderson, would often come in and join us, and he would be invariably bruised and bloodied from fixing all the breakouts that occurred during the day. And he would say, referring to the coil anchors, those damn things should be chained together. Well, that kind of caught on, and it led to the Thomas E. Anderson Memorial Award here, which for a number of years at Atlas was presented to the Atlas Employee of the Year at the annual Christmas party. And we got a kick out of that. I don't think Ed appreciated it very much, but the Atlas employees enjoyed it. Obviously, we had to develop a bearing type anchorage, and that was done primarily by an Atlas employee by the name of Dick Martyr, along with help from Hal Long, president of Atlas. And this was the very first ductile iron casting that was ever made and used in the United States. It was first used in 1963 by Atlas. It was kind of interesting. We had a basic rectangular shape, 2 inches by 5.5, which gave a gross area of about 11 square inches, less the holes, and that was adequate for stressing at about 3,000 psi. It incorporated the tapered hole, which accepted the wedges, and interestingly enough, and by the way, that rectangular shape was so it could be used in very thin slabs. There were a lot of 5-inch slabs that were being used in parking structures at that time, and this 2-inch dimension just worked beautifully in a 5-inch slab. We got what I thought was a brilliant idea to manufacture these things in groups. They were castings that had, obviously there was a single shape, there was a double, the H222, 322, 422, and we actually had, mostly for beams, we had a group of castings that would accommodate 5. And the iron workers used to just love this because you could place a 522, 5 anchorages for about the same cost that you could place a single anchorage. But it never caught on, and no one has ever used, to my knowledge, no one has ever used multiples since Atlas in the 60s. Here's what the system looked like. The 7-wire strand passed through the anchorages. The strand was greased and plastic sheathed. These are the grippers, which are very similar to grippers that are used today. And our stressing pocket we called a grommet. It was a 2-piece rubber assembly, not the single plastic piece that's used today, but it was 2 pieces. We thought it was easier to handle with 2 pieces. That never caught on either, but the rest of it did. We used small, beautiful, lightweight open throat stressing equipment. Most of it was developed by Dick Martyr for Atlas. You can see the very lightweight. The typical stroke was 8.5-inch stroke, and it only weighed 39 pounds. So easily handled by one iron worker, and again it was open throated so it could be attached to the strand at any point along the length. For a while there was a vicious commercial battle then between the Strand system, which was used by Atlas, and the button-headed Tendon system, which was used by everybody else. That would include companies like Prescon, Ryerson, Western Concrete Structures. But after a very, very fierce, nasty 7 to 8 year struggle, by the late 60s, we at Atlas had won the battle of the marketplace, and button-headed tendons became extinct, really, never used again. And virtually all building post-tensioning has been with strand tendons ever since the late 1960s. Interesting to note what happened to lift slabs. Again, I said that the post-tensioning industry owes its existence to lift slabs, but we hardly ever see any lift slabs anymore. The problem was one of greed. The lifting companies, remember, they all had a license to market the button-headed tendon post-tensioning system, so they combined the lifting and the tendons in their bids. Now that excluded independent post-tensioning companies, post-tensioning companies that were not lift slab companies, like my firm, Atlas Prestressed Incorporation. That excluded us. We couldn't bid on a lift slab job. So independent PT companies were shut out on every lift slab job. What did we do? Well, in one of the better business decisions that I think was ever made, we formed alliances with what was at the time the emerging flying form industry. I remember there was a big, wonderful company called Formies, and I think they were based in Albuquerque, and we had developed a very close relationship with them. And along with very progressive concrete contractors, we would jointly, between post-tensioning companies, flying form companies, and progressive concrete contractors, that allowed direct competition with lifted buildings. We could compete directly with lifted buildings. Cast-in-place post-tension buildings using large panel flying form systems became highly competitive with lifted buildings, and by the late 1960s, cast-in-place buildings became preferred, and lift slab buildings became virtually obscure. I think it was a very short-sighted decision on the part of the lift slab companies. If they had not originally tried to exclude independent post-tensioning companies, it's possible that large panel flying form systems would have never been developed or refined to the extent they are today. And I think lift slab construction, if the lift slab companies had allowed competition from the independent post-tensioning companies, I believe lift slab construction would be a significant factor in today's medium-rise building market. There are some complications in that. There were some very serious lift slab accidents during construction that may have affected that statement, but I still believe it to be true that lifting was an excellent method of construction. It eliminated forming, which is one of the largest costs in concrete building construction. Interesting to know how much post-tensioning is done in the United States, or has been done. And based on tonnage statistics from the Post-Tensioning Institute that started in 1972 and reasonable estimates of what happened before that, there have been about 5 billion, that's with a B, billion square feet of building construction done in the United States with unbonded post-tensioning. And that includes, if you assume about 100,000 square feet per building, that assumes there are about 50,000 post-tension buildings in the U.S. Most of those are still in service. And again, that does not include bridges, earth applications, or residential foundations, which is the largest application of post-tension tendons in the country. Larger than all other applications combined, post-tension residential foundations on expansive soils. Looking back over my half century in the post-tensioning industry, I would say that the following are the major landmarks that occurred that contributed to the growth of post-tension concrete in buildings. First, of course, the introduction of the Strand system, which replaced the button-headed tendon system. Next, the development of the ductile iron casting for single-strand unbonded tendons. We've talked about both of those. Third is the introduction of what was called the load balancing design method. That was done by T.Y. Lin in a paper that appeared in an ACI journal in 1963. Next came the introduction of what's called the banded tendon layout for two-way slab systems. Finally, the formation of the Post-Tensioning Institute, tremendously important landmark in post-tension buildings, and that led to great improvements in corrosion resistance, which I'm going to point out was the biggest problem that the post-tensioning industry ever faced. What's the most important single development? That's a tough one, but I would have to consider, all things considered, I believe that the most important single development or landmark in the growth of the post-tensioning industry in the United States is the introduction of the load balancing method by T.Y. Lin in 1963. It's also called the equivalent load design method. Now, T.Y. wasn't the first to use it, but he did more than any other individual to explain it and disseminate information about it. It made the design of prestressed concrete as easy as the design of non-prestressed concrete. The tendons became just another load. Once you remove the tendon and replace the tendon with the loads that it exerts on the concrete, now you've just got a concrete member that has a system of loads. Some of them go in unusual directions, but they're still just loads. And that made a huge difference for the designers. It encouraged the selection of post-tensioning as the preferred structural system. Building codes, of course, are extremely important. Structural engineering is one of the few professions in the world that is completely governed by laws. No other profession that I'm aware of is completely governed by laws. Structural engineering is. Post-tensioning was virtually absent from the 1971 version of the ACI building code, ACI 31871. In fact, in that code, the structural engineer was told to ignore secondary moments. It's the only code requirement that I'm aware of in my entire career that requires a violation of statics. I joined ACI 318 in Committee 318 in 1973. Partially because of my influence, the next two codes were greatly improved, 77 and 83. They reflected testing on banded two-way slabs at the University of Texas, and post-tension beams with both unbonded and bonded tendons at the University of Washington. They addressed the banded tendon distribution. They addressed minimum bonded reinforcement requirements in both beams and 1- and 2-way slabs. And they paid much more attention to indeterminate structures, which of course includes most post-tension members. And again, the codes have continued to improve with increased expertise on ACI committees. I consider several major construction innovations and advances to have occurred during my career. And perhaps the two most significant were what happened in high-rise construction in the state of Hawaii in the 1960s and 70s, and of course the introduction of the use of banded tendons in 2-way post-tension slabs. Let's go to Hawaii. Okay, no objections. Here's a picture I took from the Ala Moana Tower in 1977 of the kind of looking back towards the mountains, Mauka. And it's interesting that virtually every building that you see, every multi-story building that you see in that picture is post-tensioned. Hawaii was a fantastic market in the 70s for post-tensioning tendons. Here's the reason. Timing was just everything. At that time, there was a huge input in foreign investment. Both China and Japan started to look at Hawaii as a very favored vacation spot, and they wanted to cash in on the opportunities for providing hotels and condominiums in the islands. So there was a tremendous construction boom in the islands in that time. It was a very slow time on the mainland, but it was booming in Hawaii at that time, both in high-rise hotels and condominiums. And again, the faster you could get these buildings completed meant the quicker you could get them rented or sold, and that meant more revenue. So construction time became the most important factor, or the top of the list, certainly. Now, in these high-rise buildings, obviously the vertical elements, the columns and walls, dominated the critical path. You couldn't do anything until, you couldn't build the next slab until the columns and walls were completed to the soffit of that slab. So what's the solution to that? Well, build the columns and walls out ahead of the floors. And thus the area of jump forms and flying deck forms arose. This is a multi-story building just starting out in construction. You can see that none of the elevated floors have been cast yet, but the walls and columns, or the walls in this case, are up about 3 levels. How do we do it? Well, we hung the slabs from the walls. We provided holes. The Hawaiian word for a hole is a puka. We provided pukas through the wall through which the slab reinforcing passed, and that was fully adequate to support the slab from the walls after the walls had been erected above the slabs. And with this type of construction, we could actually get the schedule down to 3 days per floor, which was spectacular. In a typical schedule, the slab concrete would be placed on a Monday morning. The walls and columns, remember now, are 2 or 3 lifts above. The tendons would be stressed on a Tuesday morning, one day. Oversized anchors, 4x6 anchors, were used to allow stressing at 1500 psi, which we could achieve in 24 hours. The forms would be flown. Once the deck is stressed, it's structurally adequate. The forms could be stressed then on Tuesday after, the forms could be flown, removed and flown on Tuesday afternoon, set above the stress slab. The tendons and rebar would be installed on that next slab on Wednesday morning, again placed through sleeves in the walls and columns. The slab concrete again would be placed on Thursday morning, and that's Monday, Tuesday, Wednesday, Thursday. That's a 3-day cycle. We did a bunch of beautiful multi-story buildings in the 40 to 50 story range in Honolulu in that time period, all using some type of jump form, slip form system where the walls and columns were built out ahead of the slabs. The next major construction advance was the introduction and development of the banded tendon system in two-way slabs. And it's interesting, it was first used in the most famous post-tension concrete building that has ever been built. Not because it's post-tension, but because of what happened there. It's the Watergate Apartments in Washington, D.C. It was completed in 1968. At that time, a system called the basket weave system, tendon layout, was being used for two-way slabs. Some tendons were in column strips, an imaginary strip that's centered on the column. Some were in middle strips, the area of the slab between the column strips. The tendons, of course, were draped in a curved vertical profile, which was high at the column lines and low at midspans. So a single tendon profile had some perpendicular tendons above it and some below it. And this is what that looked like. In this section, the tendons near the column at any one point in the slab would have only tendons above, and that meant they were sequence number 1. They had to be placed first. Then the tendons in the perpendicular direction that passed directly above sequence number 1 but below sequence number 3 had to be placed. That was sequence number 2. And then the rest of the tendons were sequence number 3, and they could be placed. And you had to place them in this sequence or you couldn't chair them. You'd get a bird's nest of chairing. So the detailer in that time period with the basket weave tendon system had to find the single tendon which was below all other tendons. That was sequence number 1. Then he or she had to find the tendon in the perpendicular direction, which was below all the remaining tendons. That was sequence number 2. And a typical slab would have 30 to 40 sequence numbers. Even relatively simple slabs would have 30 or 40 sequence numbers. And here's what a basket weave slab looks like. It isn't actually a slab, it's a two-way mat foundation, but it really exemplifies the potential problem with the basket weave system. You can see where the arrow is pointing that particular tendon that the arrow is pointing to goes under some of the tendons and over other tendons. Again, the tendons had to be installed in a precise sequence, and any error in a placing sequence resulted in a bird's nest when it was chaired. You'd have to pull the tendon out and rethread it. Back to Watergate. In the Watergate building, the columns didn't line up in either direction. The spans were very short, only about a 22-foot maximum span, but the columns were located where they could be hidden with no regard to a grid system at all. The building was curved to further complicate it, so there were no grid lines. The column locations were actually identified by coordinates in Watergate. The column middle strip concept, of course, was meaningless, and the load path was virtually impossible to follow. So what did we do? The slab design engineers was a conglomerate of 2i Lin and Atlas Prestressing Corporation. It was a design-build project. We conceived the load path in the only way we could as a one-way slab. We developed a tendon layout where all of the tendons in one direction were placed in a narrow, bent, curved band that were connecting columns, like a beam. And all of the tendons in the orthogonal direction were uniformly distributed. Now, the load path was easy to follow. It was really just like in a one-way beam and slab system. It worked. It was scary, but it worked. And it had a number of fringe benefits. It resulted in a substantial savings in labor costs. The placing contractor, the tendon and rebar contractor, was ecstatic about it. He said that of course, it eliminated tendon sequencing. All the band tendons get installed first, then all the uniform tendons get installed next. And the banded tendon system has become the standard method for tendon layout in two-way slabs now, ever since Watergate, really, for more than 40 years. There have been hundreds of millions of square feet in service, and the behavior has been studied and verified in numerous laboratory tests. This is one of those tests. This was a picture I took in the early 70s of a 4-panel test at the University of Texas at Austin that was conducted by the famous and revered researcher and professor Dr. Ned Burns. Banded two-way slabs are magnificent in their simplicity. Here's a simple light tendon layout in a below-grade structure. Here's a simple but heavy tendon layout in a podium slab. And of course, here's the biggest advantage. This is in a very complicated tendon layout with all kinds of curves. The banded tendon distribution in this type of structure is indispensable because it really allows you to precisely define the load path. Now, I like this one. No discussion of the history of post-tension concrete could possibly be complete without a discussion of the use in computers in post-tension concrete design. When I graduated from UCLA in 1963 and started my first job with T.Y. Lin and Associates, this was my primary mathematical tool. It was a slide rule. It could multiply and divide, but it didn't know where the decimal point was. I had to figure that out. Now, I can do a dynamic analysis of a 40-story building on a flight between San Francisco and Los Angeles on a laptop computer about the size of a book while sipping a glass of Cabernet. I'm just kidding. Of course, I'd never do that. It would probably be Merlot. No. With all the decimal points in exactly the right place. Just in one lifetime, the changes in computing power have been astonishing. From slide rules to personal computers the size of a notebook, and with more power than mainframes that took up an entire large room. I said in this building because I often give this presentation at UCLA, and that's where it started. Let's take a look at my personal journey through this really whirlwind of technology. This was my first introduction to machine-assisted calculations. This was the Olivetti Programma 101, which was introduced in 1966. So I was with Atlas at the time. We did a tremendous amount of design at Atlas, along with supplying the tendons. We recognized that the most effective way to market post-tensioning was to teach engineers how to design it. So we had a large staff of over 100 licensed engineers at Atlas, and we would provide both design build services and design assistance for structural engineers in their office. The Olivetti Programma 101 was really a very large hand calculator. It showed the power of machine-assisted calculations, however. It had machine language. There was no computer language. You would enter a number, it's like a calculator. You'd arrow up into, you take it from the X register to the Y register. You divide or multiply and then store that answer temporarily in another register. You could record program steps on magnetic strips, like a macro, but it would be very limited and very brief. The input and output would be printed on a roll of calculator paper with single column strips, like a cash register. The output strips would be trimmed and taped to pre-printed calculation sheets. For a short period of time, scissors became a primary structural design tool in the 60s. Here's what our pre-printed sheets would look like. Note this was done in 1972, and I had the audacity to call this a computer example. This was from Atlas. We would pre-print the variable titles on the calc sheet. That would be, there was a calc sheet for a beam and for a slab, and that would be all of the, like for example in the upper left hand corner, we would have the load criteria, the slab thickness, the width of slab, the depth, the tributary, all of the important variable parameters for the slab. And then we would run the calculations on the Olivetti. We would trim the output, the paper output, and glue it to the, or tape it to the pre-printed calculation sheets in the proper form. And again, this was a big improvement over doing calculations by hand. The next major landmark in computers was the introduction of the Wang 700 series of, they were called computers. That was done in 1970. But it was a very large supercalculator. It was still machine language. Enter a number into the X register, arrow up to the Y register, do something, store it. It could record the program on audio cassette tapes, which was much more capacity, but it was read-only. You couldn't write to the tapes. It had much more capacity, more registers, places to store stuff, and you could print with a modified IBM Selectric typewriter, so you had the advantage of columns and a much prettier format. With the Wang 700, we could write a crude analysis program in a series of independent routines. The answers and some of the repeated input from one routine had to be used in the next routine. So there was a lot of reuse of numbers. It was not a design program. You couldn't do a true design. You had to do a series of analyses to get to a design answer. You would input a first guess at geometry, force, and profile. The machine would perform an analysis. It would calculate stresses and rebar. If you weren't happy with that analysis, you'd change something and then do the design again, or do the analysis again, iterating to an acceptable design. The moments and shears were calculated with a 2-cycle moment distribution routine, either by hand or with a programmed routine. There was, of course, no possibility for matrix inversion. The first real personal computer appeared in 1973. It was the Wang 2200. It had, for the first time, a basic language. It had a basic interpreter. Now we could do loops, decisions, if this, then. It had a mighty 4 kilobytes of RAM, so it required tedious programming. You would input some data, you'd do some calculations, you'd print the answers with a Selectric typewriter, you'd delete the unneeded data, you would input some more data, you would do some more calculations. So it was tedious, but again, it was better than doing it by hand. The program code was recorded on audio cassette. It was read-only. The output again was printed on 8.5 by 11 sheets with a modified Selectric typewriter. And that again meant we could use tabular format with alpha headings. The output became much more usable. And again, all subsequent programming became easier. If you could program the Wang 2200 with 4 kilobytes of RAM, you could program anything. 1981 changed the world. IBM came out with the first personal computer, the PC. It had 2 floppy disk drives. It had a monitor, and you could print to a dot matrix printer. It allowed you to read and write to the 2 floppies. It had 64 kilobytes of RAM. It had a processor speed of 4.77 megahertz, did not have a hard drive, and it did have a basic programming language which was developed by Microsoft. 1983, a huge improvement was the introduction of the IBM XT, and the biggest factor in that was it had a floppy disk drive and a hard drive. It was the first PC with a built-in hard drive. It was 10 megabytes. It had 128 kilobytes of RAM and the same processor speed, 4.77 megahertz. The XT allowed vast improvements in post-tensioning programming. It allowed the use of matrix methods. It could be used to develop a true design program with iterations. It had much more sophisticated routines like punching shear. And we didn't have to spend so much time juggling and printing data. We could actually do refined calculations. And of course, the world changed again in a massive way in 1985 with the introduction of Windows by Microsoft. Windows replaced DOS as the prevalent operating system. It was originally a 16-bit program with Visual Basic as its language in 1985. And now third-party programmers could use not only Visual Basic, but all of the beautiful Windows fancy interfaces and input-output routines. Windows changed to a 30-bit system in 1994. That required major conversion for 16-bit programs like ours, PT Data. Again, it changed to a 64-bit system in 2009 with the introduction of Windows 7, and it changed to Visual Basic Net, a 64-bit system. And that required another major conversion for 32-bit programs. It's just astonishing to think of the changes that have happened since the first personal computers were introduced. Just look at RAM. It went from 64 kilobytes to 4 gigabytes. That's an increase of about 60,000 times. The processor speed increased over 300 times from 4.77 megahertz to 1.4 gigahertz. And the disk storage, the change in disk storage was just huge, from 10 megabytes to many more than 1 terabyte now. I think there were 15 terabyte hard drives available now. Again, it's not easy to face, but there have been some problems with post-tensioning in its growth. The first major problem was faced by the post-tensioning industry was restraint to shortening. The mechanics of restraint to shortening are different in a prestressed and a non-prestressed member. And engineers had to learn how to design post-tension floor systems with levels of cracking that are normally accepted in non-prestressed floor systems. We didn't have to eliminate cracking, that's impossible, but we had to get the levels of the normal levels of cracking in post-tension floor systems down to about the same level which engineers had come to accept in non-prestressed floor systems. The predominant methods that were used to solve those problems were the use of joinery details. It was not mathematics. Math didn't solve this problem. The thing that solved the shortening problems were joinery details like slip joints and pore strips, and the effective use of non-prestressed reinforcement that would distribute the cracking that did normally occur. But by far the biggest problem that has ever been faced by the post-tensioning industry is tendon corrosion. The early sheathing in grease was inadequate for the aggressive corrosion environments. That would be environments primarily where de-icing salts are applied to the concrete, or in ocean environments. Now, material specifications, improved material specifications developed by the Post-Tensioning Institute have largely solved the early corrosion problems. And that includes improvements in sheathing material, in coatings, and finally, the complete encapsulation of the tendon. What's in the future? Well, from my standpoint, after 50 years, what I've been doing up to this point is looking backwards. Now I'll take a little look into the future. I think that there are two major things that I see that will apply that will change the post-tensioning industry in the future. The first is the strengthening of existing buildings with externally applied post-tensioning tendons. It's a very green concept. It involves retrofit of existing buildings versus replacement. And that extends the useful life of a building, and that fits well into our world of sustainability. The second thing that I see in the future area, a huge area of growth, is in tall concrete buildings. Strengthening with external post-tensioning is really exciting. It's a fantastic area. Our firms have completed over 70 projects with external post-tensioning. They have been very, very successful, and in many cases they saved the building from being demolished. External post-tensioning systems involve building a king post truss under the structure. We drill through the existing structure, apply what we call a saddle, which is a structural steel assembly, at the point where we want to apply the beneficial load to the structure. We string the tendons through the holes that we've drilled. We string the tendons below the saddle. Once the tendons and the saddles are in place and all the anchorages are in place, we stress the tendon. It tries to straighten out. It can't straighten out because it's got this saddle, and in coming to equilibrium, it applies a very beneficial load at just the right place on the structure, which increases the strength and remedies any deficiencies. Here's an example of a completed project that we did decades ago. This is in Reseda, and this one is fireproof. This is a two-way slab. This is the load being applied in the center of the bay. That load is applied by these post-tensioning tendons, which come over to the adjacent column line and apply their load down to another saddle, which is picked up by a tendon which carries its load to the columns. This project was fireproof. We've done many projects that do not require fireproofing. The fireproofing here was done with a vermiculite plaster. The plaster is applied to a self-furring metal lath, which is wrapped around all of the exposed portion of the system. The other development that I see in the future for post-tensioning is in the construction of tall buildings. There's a historic perception among structural engineers, architects, insurance companies, contractors, that tall buildings must be built with structural steel. What's a tall building? I probably more than 20 stories by my definition. But the use of high-strength concrete makes the column sizes reasonable, and the use of post-tensioning reduces the weight of the floor systems by about 30%. And that results in savings in all of the load-carrying members, the columns, the foundations, and the seismic system, either the frame or shear walls. The advantages, of course, the biggest advantage in the use of concrete in tall buildings is cost. There's a reduced height and volume. You can expose the exterior frame beams and columns and result in significant savings in curtain wall. There are advantages in fire and blast resistance, any catastrophic load resistance in a concrete building, in an indeterminate concrete building. Concrete is inherently fire resistant. You can expose, again, the exterior beams and columns, and that eliminates the vertical path for fire from floor to floor between the edge of the structural floor system and the curtain wall in a structural steel building. And that has caused significant problems in structural steel buildings as the fire is allowed to transmit vertically from floor to floor. And of course, it results in a substantial savings in curtain wall, about 25%. There are additional advantages in sound transmission and in vibration. Here's one that is very personal for me. This is a building located at 3900 Alameda Boulevard in Burbank, California. At the time it was built, which was in 1988, it was the tallest concrete building that was ever built in seismic zone 4. That is now seismic design category F, the most severe seismic category at the time of construction. I wrote an article in the PTI Journal a few years ago on this building. You can see it from my website. It's called PT Treasures. The details of 3900 Alameda, it's 32 stories. It's completely cast in place. It has a 7-inch thick post-tension flat plate floor system in the office floors and beam and slab framing in the lower garage floors. The framing in the office tower is monolithic cast in place downturned perimeter ductile moment frames. And most of the frame beams and the columns are exposed at the perimeter. That replaced about 25% of the exterior curtain wall system and greatly improved the fire resistance between floors. The other tall concrete building that I'd like to highlight today is the Paramount Apartments at 3rd and Mission in San Francisco. It was completed in 2002. It features 43 stories. It is the tallest concrete building that has ever been built in the most severe seismic design category, D, E, or F. It's the first post-tension precast concrete moment frame building in seismic zone 4. It has an exterior precast post-tension moment frame. It's the building with the first use of unbonded post-tensioning as primary reinforcement in the seismic moment resistant frame beams. And it has a two-way post-tension flat plate floor system which minimizes dead load and reduces vertical and lateral loads. It also has a post-tension mat foundation. Coming to the end, I'd like to talk a little bit about careers in post-tensioning. The transition between a highly technical specialized construction form to an off-the-shelf commodity has taken much longer than we thought. Back in the 60s and 70s, we thought that in 20 or 30 years, post-tensioning the design expertise in post-tensioning would become widespread, and post-tensioning would become a kind of a commodity, an off-the-shelf item like mild rebar. That has not happened. That transition is taking much longer than we thought. Even today, much of the expertise is still within the industry. Based on some very reliable sources, I can state that no more than 30 structural engineering firms in the entire country today are capable of independently designing a state-of-the-art post-tension concrete building without help from the industry. Part of that problem, part of the reason for that problem is in the education system in our universities today. And rather than babble on about that, I've written a very extensive paper on that expresses my not too popular views. It's found on my website, www.kenbondy.com. Go to the professional page, and the paper is called The State of Post-Tension Concrete Education. I think, based on the present situation, looking from my eyes at what's going on in the country now in the post-tensioning industry, I think that there will be 2 to 3 more generations of engineers. My son, his sons, expertise in post-tensioning will be in great demand. It will be highly specialized. And that's before post-tensioning design and construction expertise is widely available through the industry, and everybody knows how to do it. So again, for 2 or 3 more generations, it will be very valuable to know what you're doing in post-tension concrete. And if you're a student, you might want to think about this. For me, it was a great ride. Thank you very much.